Hello, everyone. Firstly, just a quick announcement. I'm not Tom. If you asked the Tom, this is Tom. He's in the other room. He's talking about web stuff. I'm Tim. That's Tom. Tim. OK. So I love Python, so much so that I may have started a conference about it. But I'm also practical. I like to use the right tool for the right job. And everything is a nail, which is what I'm saying here is that Python isn't the solution to everything. It's like the solution to almost everything, but not everything. And so when a problem comes along that Python's not suited for, I tend to not use Python for it. That's pretty simple. So the question I guess this talk is trying to answer is, should you use Python for hardware? And it's kind of an interesting question. Python is a very long way away from hardware in many senses. As the keynote this morning demonstrated, CPython is not designed to run on small devices. It's definitely not designed in a strict write once, bake into a chip, and then leave for 20 years type design. Python's not actually that old a language. This leaves a lot of questions about whether Python is the right tool for hardware. It's definitely not the most popular tool for doing hardware in either. And generally I've found, while it's not strictly true always, the most popular tool is the best tool to use for something because somebody else has already run into the problem that you're trying to solve and posted on Stack Overflow about how they're having this problem, and you've got a solution there. So I tend to try and use the more popular tools because it makes it very easy. I don't have to think. I can just go on Stack Overflow. And Python on hardware, not a huge amount on Stack Overflow. So for those reasons, I would have said no about 12 months ago, I think. But today I say yes. And it's an interesting story to find about how I went from a no to a yes. And that story is the story of a project that I've been developing called the HDMI to USB. So HDMI and USB is part of a bigger project that I'm running called Tim's Videos. The URL is Tim Videos Us. I got tired of naming things, so I just call it what it is. And the aim is to make streaming and recording of events like this and user groups and stuff like that extremely easy, can be done with no AV crew. We're not there yet, but that's kind of our long-term horizon goal. Make AV people obsolete. Well, they can go and do some more interesting things. So this is how you stream a conference. Turns out there's lots and lots of Python in streaming a conference with the stuff I've developed. As I said, I like Python, and Python is a good tool for lots of things. We have a hardware mixing solution, which is mostly Python. We have capture stuff, which is Python. Streaming system's Python. The website the streaming system goes into is Django. We're at a Python conference, so I guess even the content's Python. And I'm a little bit Python in the head sometimes. But there are two things that I didn't point to in that very quick thing, and that these two things here, which are the HDMI to USB devices, they're an actual piece of physical hardware. They look like this out of a box. If you have been a speaker or you're sitting close, you can kind of see there's another one in the box down the front, and there's one up the back connected to the camera as well. Their job is to take HDMI signals and convert it to something a computer can use. Some ways it's kind of weird that a computer can produce HDMI signals but not really accept them. But that is the problem that we need to solve, because the HDMI signal is how people project So this is the hardware that makes up the HDMI USB. We currently support 2 different development boards. They are centered around a thing called FPGA, which is a field programmable gate array. The really cool thing about a field programmable gate array is it makes hardware problems software problems. And I'm a software developer, not really a hardware developer, although I pretend sometimes. And I like being able to make a mistake and not cost $100 million of failed chips. So software makes it much easier to do that. I can update. That's the awesomeness of an FPGA. Problem with FPGAs is that they're programmed with 2 major languages. One of them is called Verilog, and one of them is called VHDL. You might notice neither of these are Python, sadly. Just a background on Verilog. Its syntax is C-based. You can kind of see it's been around for a while. 1984 was a key date for it. It's a kind of weakly typed in the same way C is. It lets you do all types of nasty things like cast things through the equivalent of void pointers. It has really good open source support, which is kind of interesting. There are a lot of university projects which have released open source interpreters for Verilog. So you can make your computer interpret a language for describing hardware so that you can see what hardware is going to do on your computer. That's pretty cool. Yeah, but it's still not Python or even Python syntax based. The other one is VHDL. It's based on Ada. Who knows what Ada is? A bunch of you. Ada is an interesting language. It's not very popular, except in, say, defense. VHDL is also newer than Verilog. As you can see, 1987 is a key date for it. It's a much more strongly typed language, but kind of like Ada, it's extremely verbose. You kind of think of it like the Java side of things. It's good in lots of ways, but also not good. Has extremely bad FOSS support, but has one really cool thing, which is determinism. That is really awesome for making hardware. Verilog is kind of a little bit suspect in that area. Again, Ada is not Python, or even looking like Python at all. So because of the reasons I stated at the start of the talk, I went with designing the firmware for our FPGA to do HTML capture using basically a bunch of pre-built stuff written in VHDL and Verilog. It supported this board here, and it kind of works if you squinted at it sideways, and were very kind to it. It worked. It took about 3 years to do that. There are lots of features on this board that you can kind of see. There's like an Ethernet and some audio and all this type of thing. None of them were supported by the firmware yet. It just did very basic HDMI to USB translation. It also had a problem around licensing. Lots of the FPGA manufacturers will release designs that work on their hardware. You can use them in your own designs, but they require you to use it on their hardware. So if you want to use one of their competitors' FPGAs, you can't use that design. So it's not really open source well, it's open source, but it's not really free software type thing. And that's kind of sad. It also was not very well tested. Verilog and VHDL people have interesting ideas about testing. They're not software developers. The idea of continuous integration is a new and exciting field for developers in this area. I guess for them, you verify it works once and then you never change it again. That tends to be a pretty common occurrence. For us, we wanted something that was evolving and continually improved so that every time somebody has a problem with a presentation, or like us capturing something, next time we get the capture, it doesn't fail the same way twice. We want to improve it. And like that's what we need to be able to make AV people obsolete. The reason AV people exist is because in their head, they have all those random tricks that make this little box work in the way that it's actually supposed to, but never quite does if you connect things slightly wrong, or it's kind of like the Windows reboot type thing. Then, as I said, we're kind of developing on this Atlas board, but this Atlas board isn't open source. It's a proprietary development board that you can buy. And I'm an open source person. And I wasn't content with just making firmware. I wanted my whole system to be open source. As well, there are a whole bunch of downsides of using a development board. A development board is designed for development, not for deploying in production. And so we made our own hardware. It's called Opsis. This was our crowdfunding campaign, which is now finished. This is kind of where you can get it. The interesting thing about this board and the Atlas is they're very, very similar, but not identical. They have very, very similar FPGAs. They have very similar USB interface, very similar HDMI interface, all these type of things, but they're not identical. And we couldn't make them identical and still achieve our goal, which was making something that's better for production. The boards were different, which means the code that runs on them needs to be different. Both Verilog and VHDL make it very hard to do what I think of as simple things, like making modules that say, okay, I want 3 of these instead of 5 of these, and I actually only want it to use 3 times the resource on the other board and 4 times the resource on this board. You can turn on and off features, but they generally use the resources that you want to get back, and just generally, they're not very good at building modular software or doing continuous integration. And again, still not Python. And so while I was despairing about how long this project was taking and how it was going to take me another 20 years to do this, I came across this piece of hardware. This piece of hardware is called the Mixxeo. It has a very similar design to our board. We'd never seen each other's boards before, but this kind of you know, when there's this idea that at a certain time period, ideas become fruitful and everybody comes up with ideas at the same time, this was kind of that. They had come up with a similar type of design for a totally different use case. This was for video DJing rather than video capture at conferences, but very similar design. And they had done something that I didn't think made sense, and that was do a lot of things. They developed their own DDR RAM controller. I had used the one supplied by my FPGA manufacturer. You know, they probably know the best way to configure their own hardware. They've done things like make their own Ethernet controller, all these type of things. They had support for 20 boards. But the one thing you're probably all looking at is this thing. That is Python there. So since these guys had tried it, I was less skeptical. I had kind of an inkling of hope that maybe I could do Python. This was kind of before things like MicroPython and in a very different domain. So still very skeptical. But the Verilog and VHDL were terrible enough that I was willing to entertain that skepticism. My hypothesis was this was going to be a pipe dream. It was never going to work. So the first thing that makes me even more skeptical is that to run an FPGA, you need to be compiled onto an FPGA. The tool chains that take code and compile it and let you load it onto FPGA, none of them understand Python, and they're all proprietary, and you can't get access to how they work or any of those type of things. And so how do you develop Python that fits into this thing? What you're actually doing is generating Verilog using your Python. And then their system takes the Verilog, which you don't need to deal with because you're dealing in a nice Python world, and converts into stuff on the thing. So you're kind of still dealing with Verilog, but you get to deal with Python, and the Verilog is kind of just a translation layer that you don't really need to worry about. So what I did was, I didn't have time to do it myself. I decided that I would throw money at the problem. Basically, instead of buying a new laptop, I would fund a guy in Europe to rewrite the functionality of our firmware using MiGen and the MiSoC technologies. And it took him 4 weeks. It had more features. It had buffering so that when the video is written in, it's written into a buffer and then read from a buffer, which means that if I disconnect my laptop now, the projector still continues to get signal. So if you've ever had that problem where you disconnect from a thing and then the whole system decides, oh, you've disconnected, I'm shutting down the room, and the projectors go up. That doesn't happen because as far as the projector is concerned, it's still getting a signal. I mean, it's a black square, but it's still a signal. It supported both our boards. It has a CPU inside it, basically a Softcore. It has Ethernet. The thing I hadn't realized at the time was how awesome having a Softcore in the firmware was. It meant that we could write C code for a lot of our functionality that we used to have to write hardware stuff for. And writing C code is much easier than writing hardware. You can compile it with GCC, and you can update it really easily. It's a much faster development cycle. I don't know. Somebody could probably port it to the Softcore. That's Joel. He's just volunteered to port MicroPython to it. We also can support 2 different types of Softcores. And I'm running out of time. It does have some downsides. Those Softcores aren't part of the standard toolchain you get on a Linux system, so you need to compile them yourselves. The LM32 is upstream, but again, not something you can get installed on Ubuntu. And the community is a lot smaller. Like, it's not like x86 or ARM, which have a huge number of developers for. But you can kind of see that our original firmware, which was VHDL and Verilog based, was hard to extend, had questionable licensing, had all these problems. Our new firmware, the MiSoC firmware, is Python-based, has a lot more functionality. We really use Python's ability to express the differences between the boards so that it generates totally different Verilog output, which means that it's custom for that board. We're not wasting the resources because the boards are different. If a board doesn't have an Ethernet controller, the code for the Ethernet controller never gets generated in the Verilog, and so it can never take up resources. The other great thing about it is everything they did is released under a BSD/MIT license. So, and it's under a clear license. It's not under this kind of license. So yeah, it's been really awesome. There's a lot more awesome that we could do. We're slowly making progress, and doing this has finally been what's allowed us to deploy this device in production. We're using it right here now in PyCon AU to do the recording. We used it at LCA, linux.conf.au at the beginning of the year. It's been used at DebConf. I don't think we'd be at this stage without having gone down the route of using Python to develop hardware. So that's pretty awesome. Yay, Python. But this is a 30-minute talk, not a 20-minute talk. So I've got a little bit more to say. Turns out that, again, using Python to develop hardware is one of these simultaneous ideas. There are two systems you can use to generate hardware. The MiGen one we're using was selected because a lot of the infrastructure we needed, like the HDMI and the DDR and stuff, were all already available. And there's also this thing called MyHDL. In many ways, MyHDL is a better, more purer way of doing things. It's also been well tested by other people. People have used it to actually generate stuff that's been made into production on real ICs, not just FPGAs, but real ICs. So both these are pretty cool. But there's still more. The thing is, to make hardware is also a reasonably complicated process. And to do that, you need things like schematics and the PCB, like the printed circuit board that needs to be drawn and all that type of thing. And so me, again, being an open source person, I use a tool called KiCad, which is an open source tool for doing schematic and PCB design. Our OPSIS board was designed in KiCad, and you can go and check out the hardware design. And if you have the ability, you can actually make your own if you wanted. It's all CC by SA licensed. KiCad is scriptable in Python. And the KiCad files are plain text. And everybody knows that Python's really awesome at generating and passing plain text. So FPGAs need this thing called a UCF file, which basically says this pin is connected to this other device, and these are the voltage levels that they talk to each other, and that type of configuration. Normally the way you do this is you get somebody to sit down and write this file looking at your schematic. If your schematic changes, then your UCF file is out of date. And then you spend weeks going, why can't I talk to the Ethernet controller? It's because you're using the wrong pins. And so the way we do it is I have a piece of Python code that passes the schematic, looks for the FPGA component, and then traces all where the pins go. And oh, look, this one ends up over at the Ethernet controller, so let's generate a bit of UCF that does the correct things for the Ethernet controller. So in this way, Python is helping me do hardware. I have this kind of dreamy goal to eventually bring continuous integration and unit testing to circuits. They have some type of basic thing called design rule checks. They generally just check that you haven't connected a power input and a power input together. I'd like to do much more advanced things, like if you connect the wrong pins in the HDMI connector to pins on the FPGA that don't support this, rather than going, yes, you're good, it goes, this doesn't work. And that allows you to quickly iterate on your designs more. So I've kind of started this circuit unit test. It's not particularly well done yet, but there's that kind of another idea of using Python for hardware. So that's actually at the very low level of making real physical objects and making them work and doing it faster. Like developing hardware has this lead time that when you get it wrong, you send it off to manufacturer. Maybe if you paid a bit of money, you get it back a week later. If you didn't and probably a couple of months later. And when you get it back and it doesn't work, well, not only did you lose money to make it happen, it's another period. Imagine what it would be like developing software if your compile times were a week long. So Python can really help. But there's even more. Hardware generally works better when it's talking to other things like your computer. And the two most common interfaces these days, like physical interfaces, I guess there's Wi-Fi as well, are USB and serial. And Python is awesome at both. pyusb is the really good solution for talking USB. It supports a whole bunch of the libusb-C stacks. It's really good in that it supports back to Python 2.3 for some reason, 2.4 if you're using really ancient versions of Python. Also supports Python 3, Mac, Windows, Linux, and I'm pretty sure BSD, but I don't know anybody who's using BSD, so I can't tell you whether it works. That's kind of what it looks like. It's very low level. You have to understand the USB protocol to write this, but lets you do things like develop a prototype driver for talking to your USB in exactly the same way you might do C. So yeah, there's some downsides, but yeah, it's pretty good. We use it on, again, our board because our board has a programmable USB controller. This programmable USB controller can pretend to be lots of different things. It can pretend to be a serial port or a JTAG programmer or a webcam. This makes it kind of hard in that, well, I want it to be a webcam, but it's currently a serial port. I need to change that. Or what is it in now? It could be one of these 10 things. So we use libusb to provide a tool for detecting the boards connected. Like this is pretending to be a serial port, but it's really our board. And for switching the modes. So that's all Python scripting. As well, most of the time when you're doing USB, you're not really care it's USB, it's pretending to be serial. And so pyserial is also a great way to talk to hardware. It has even better support than libusb. It supports random things like Jython and IronPython. It's pretty easy. It's just like reading and writing a file. In many ways, except there's a few extra complications around like the speed you're writing and that type of stuff. So our device appears as a webcam and a serial port. And the reason it appears as a serial port is that it lets you control the device and get debugging information. You might have seen some of the issues that we've been having at the conference. I'm able to see what's going on by using the laptop that's connected to the device and looking at the HDMI stream and going, oh, the reason it's broken is because of this, or they're sending the wrong resolution, or all these type of things. It gives me an insight into what's happening in the box, which could be, in future, programmatically controlled by pyserial. We could have a little GUI that lets you see what's going on. So yeah, we really want to make presenting, recording, and live streaming reliable and easy. And the only way we're going to do that is by having tools which give us the ability to iterate quicker, develop new hardware, and to understand what's going on in them. It's very hard to, I can't buy a commercial device under the, 10,000 USD dollars that will give me any type of diagnostics about why it's not doing the thing that I paid $10,000 for. And I can't give a $10,000 device to a user group to record their 1 hour a month. And so, yeah, Python is essential into making this hardware happen. And because we're at a Python conference, we need your help to make this better. There are a lot of things we can do. You don't need to know hardware. For example, if you know how to make Python GUIs, we would really love help making that Python GUI work. And the serial protocol is really easy. If you can do that, that would really help us. And I have a tendency to send hardware to people who do stuff. So if getting shiny hardware in the mail tickles your fancy, come and help us out. We'll be at the sprints. And so that's my talk.
Thank you, Tim. We'll open it up for questions. Actually, I have a question. What does the hardware cost?
So this iteration of the hardware is about currently $400 US, which is a lot higher than we want. Like, I want a device like the Raspberry Pi level cost eventually, but you know, that's a lot cheaper than a lot of other devices with similar capabilities. And it's all open source. So if a Chinese manufacturer wants to make a version of this device for like a teeny amount of the cost that it costs us to make it, that would be really awesome. Please do that. If you want to make a cheap Chinese clone, please do. I want the hardware.
How do you handle timing closure in the FPGA?
That is a complicated thing to answer, and not one I have time to answer right now. The same way we do it in, if you're doing it in Verilog or VHDL, the MiGen doesn't abstract away the fact that it's still hardware, so you still have to worry about things like clock domains and getting from one clock domain and that type of thing, and then how fast you can run that stuff at and getting it fast enough to meet your timing requirements. You still have to do all that, but because you're doing it in Python, it's just much nicer to be able to change things quickly. Like if you change the size of a bus in one part, the other side doesn't all of a sudden fail to compile because your bus is now 32 bits wide instead of 31 bits wide. And you only had to change one place rather than two places. And things like that, like the two Python modules, when you connect them together, they can negotiate with each other and go, well, I talk RGB and you talk YUV. Maybe we need a translator in between us. We can do things like that in Python. You can't do that in Verilog, to my knowledge. So people end up writing Perl to generate their Verilog, which is going down a deep hole. I think we're out of time.
Okay.
And I have to go and help run lightning talks.
All right. So let's thank Tim once again.